For the last 2 years, I've been hard at work developing a workflow to affordably recycle failed 3D prints. And while I've made some serious progress in that time, there's still plenty of work, research, and experimentation to be done, especially as at-home filament recycling is about to become much more mainstream. So in this video, I'm going to tackle some of the lingering challenges that plague DIY filament recycling setups like mine. And stick around to the end, because I do think that I've made a major breakthrough that will save you a ton of time and wasted energy should you decide to recycle your own filament. Let's get after it. The first category of problems that I want to solve involves manual labor. Now, don't get me wrong, I do believe that the value of saving this material from the landfill far exceeds the monetary value of the end product. But at the same time, it is hard to deny the critics who point out that my labor alone, not to mention the energy cost, make this whole exercise a net loss. So our first order of business is to figure out how we can reduce the amount of manual labor that goes into recycling each spool. But before we do that, let me give you a real quick refresher of the process as it stands today. So first, we start off by breaking failed prints down into manageable chunks that can fit into my shredder. Second, we shred it in the shredder, which fortunately I have already optimized and upgraded throughout the last few videos in this series to the point where it no longer really needs much babysitting at all from me. Third, we have to sift the material to remove any large chunks that could jam the extruder screw. Fourth, we use a magnet to manually remove any metal shavings or flakes from the material. From there, it's over to the microwave, which I use to quickly and effectively dry out the material. And finally, after all that, we're ready to extrude the material on the ArtMate Mark III extruder. Now, if my regrind is uniform and clean enough, it can run pretty much unattended, and I only need to refill it every, hour or so. And if that becomes a bottleneck, I have already designed a much bigger hopper in Onshape that should allow me to load about 3 kilos of regrind at a time. As of right now though, the nozzle on the extruder does clog every 100 meters or so, and I do need to go in there anyway and unclog it pretty regularly. So the hopper isn't the bottleneck. In any case, when all of this is done, with any luck, we are left with okay quality filament, but we're gonna get to that later. So as I see it, there are a few places that suck up the most of my time and attention, and we'll be attacking each one of those one by one. The first area that we can optimize has to do with sifting. While it is super satisfying to sit there and manually sift the material, it is also not a great use of my time. Now, fortunately for me, Liha Design over on Thangs has developed his very own sifting machine, which not only automates the actual sifting, but also uses an incredibly strong magnet to handle the debris removal part at the same time. Now, as you can see, I went ahead and got this entire thing all built, but as I always seem to do on this channel, I did manage to order the wrong part for one of the critical electronics components, so I won't be able to get this thing working in time for this video to go live, but after seeing Christoph's videos, I am quite confident that this thing will handle all the sifting and debris removal as well or better than I can without requiring any supervision. So let's go ahead and mark this as a check mark and move on to our next time suck, which is drying the regrind. As you can imagine, plastic that has been sitting around the studio for months or even years tends to soak up quite a bit of moisture from the air, particularly if it's being stored as regrind. For that reason, it is important to dry the regrind before you extrude it, or you will end up with pockmarked and weak filament. At least, I think it's important. But however you actually do that, whether in small batches in a microwave or in larger batches in some sort of dehydrating oven, drying takes up a lot of time. And that got me thinking, what if we could avoid drying altogether? So here's the thing. Drying filament involves heating it up to allow the moisture to escape as steam, right? And when we print wet filament, we can actually see and hear the moisture leaving the filament. So what if instead of drying the filament, we just extruded it and let the heat of the extruder remove the moisture? Sure, this would add an extra step to replace the one that we just removed, but that step can be configured to require almost none of my time or attention. Plus, this extra step might just be well worth it if it yields a commensurate increase in the quality and reliability of the filament, which leads us to the next set of optimizations and improvements.
quality and consistency.
Now don't get me wrong, if you consider where this material started off, I get pretty nice filament and even some high quality 3D prints out of it. Sometimes, if I use a 0.6mm nozzle. But there's one major issue that makes it just impossible to use this filament as a drop-in replacement for virgin material: bumps and irregularities. Though improved shredding, sifting, and isolation of questionable plastics have made this a lot less of an issue, the fact of the matter is, with a process like this, it's garbage in, garbage out. And unfortunately, it's just not realistic or practical for me to store my regrind or my failed 3D prints in airtight containers away from the normal dust and debris of my workshop. Plus, even if I did, it is inevitable that the odd fleck or purge line of PETG or ABS is just going to work its way into the mix and cause issues. In fact, I will say that my regrind is so polluted that I've actually had to do away with the melt filter provided with the ArtMay and just raw dog it. I don't actually mind that so much because I'm personally happy to only use 0.6 or even 0.8 nozzles with my recycled filament, but what I do mind is when entire prints fail because the filament just can't enter the extruder. So imagine my excitement when I saw another YouTube short from Liha Design. And in it, he demonstrates how he created a series of dies using spare 3D printer nozzles. By pulling the filament through a smaller and smaller hole, he's able to shave off any irregularities, resulting in filament that he can confidently print. So to try this out for myself, I took a handful of the extra sharp hardened steel belt printer nozzles from my Idea Former IR3 V2 and got to work. Unfortunately though, I don't have a lathe or tungsten drill bits anywhere near as precise as sizes like 2.1 and 1.9 millimeters. So I had to get creative. I sat down with Gemini, Makera Cam, and my Carvera Air CNC and figured out a way to actually machine those super precise holes into 3 different nozzles. One at 2.1 millimeters, one at 1.9 millimeters, and one at 1.75 millimeters. Now this involved creating a threaded aluminum jig to actually hold the nozzles, then manually aligning the bit, and one heroic little tungsten carbide 1mm shank. But to my utter shock and absolute pride, it actually worked. And while the nozzles weren't perfect, they were just fine for a proof of concept. So I then started modeling out different ways to actually integrate those nozzles into my workflow. Sure, Christoph was kind enough to send me his step files for his jig to actually hold them so that I could play with and adapt them to my own needs, but the whole idea of this video is to optimize the workflow to reduce the number of steps and labor required to actually make filament recycling a practical reality. So initially, I actually tried integrating these nozzles into the V-spooler filament respooler, which I'll probably be using to respool the recycled filament anyways. And it's moments like these when I'm particularly grateful that my CAD package of choice, Onshape, allows you to import and work with not only step files, but also mesh files like STLs. Now, unfortunately, the bend in the filament path made the filament catch, so integrating this into the V-spooler ended up being a bust. But from there, I uploaded Christoph's jig design to Onshape and customized it to suit the smaller nozzles and Bowden couplers that I chose to use for this project. In fact, I'll just note that throughout this entire journey, whether it's customizing complex assemblies like the precious plastic shredder that I use, or designing my own custom flanges and adapters, or tweaking and modifying existing designs out there in the community, Onshape has been my absolutely indispensable CAD and CAM solution.
Onshape is a professional-grade and cloud-native CAD suite used by engineers all over the world. Now, I particularly like it because it allows me to access all my designs from any of my devices anywhere I happen to be in the world. And I've actually been using Onshape as my CAD suite of choice since way before they ever sponsored any content on this channel. So to check them out, and if you're an engineer, get up to 6 months free of their Pro plan, use my link in the description or scan the QR code appearing on screen now. Now, let's go ahead and see how this die pulling rig actually works. Shall we?
Let's see what we got. That really puts up a fight. Let's try this again. That's a big one. We're taking off a lot of material, but that is progress. No roller. Wow, that's hard. It's not even going through. Let's try with some momentum. really hard. It's like a lot of force. All right, let's just full send it, see what happens. I think speed is gonna be the key here. All right, here goes nothing. Okay, you gotta be moving fast or it gets stuck. Speed, that's the key. If you're not moving fast, you're getting stuck. That actually kind of worked in small quantities. Let's see if we can actually print this stuff any better though.
Well, on the one hand, that was an extremely promising experiment. As you can see from this very beautiful 3D print, the filament that I did get to run through this jig is some of the best I've ever recycled. I mean, just look at how consistent the extrusion was. On the other hand, this project is contrary to our other objective in that it's very labor intensive. First of all, for now, the way that it's set up, you would need to stand there and hold the drill and monitor everything while you're pulling the filament through. Second, even if you did make it a hands-off process by, say, adding a geared motor or rigging up the drill to run on its own, it's not yet reliable enough to just set it and forget it. The filament breaks like constantly if the bumps are big enough. And every time it does, it's a huge pain in the butt to thread it back through all 3 nozzles, attach it to the spool, start it up, etc. With that said, I still do think that this is extremely promising for saving recycled filament that has the occasional bump. And with some tweaks and optimizations and improvements, this could be the saving grace that we've been looking for. But in its current form factor, it's just not reliable or hands-off enough, at least not for me. So for now, let's try something else that just might be. Which brings me back to that idea I mentioned before about just extruding the filament rather than drying it. Now, imagine if we could kill 2 birds with that same stone. In other words, what if we let an initial extrusion dry our filament and reduce the irregularities in one fell swoop? I'm talking, of course, about pelletizing and re-extruding. And believe it or not, this is a standard practice not just in the recycling industry, but in the plastics industry as a whole. After all, there's a reason that you buy plastics in pellet form. Pelletizing allows a manufacturer to achieve uniformity even when mixing in additives, plasticizers, or modifiers. Now I know this because I recently grilled Rudolph of Recycling Fabric on just how they're able to create such incredibly uniform and beautiful filament from 100% recycled material. And the secret, besides, the boring old stuff like rigorous sorting and manufacturing processes, comes down to extruding and pelletizing. But I'm sure you're wondering, what about strength? After all, don't the polymers lose some of their strength every single time they're extruded? Well, to that, I have a few answers. First, PLA, even recycled PLA, is already much stronger than we need for most of the applications that you would use PLA, or especially a recycled material for. Second, there has actually been a lot of research done on this at various universities. Now, broadly speaking, the worst results that I could find came from a 2024 study from Politecnica University, Timisoara, which found a 28% reduction in tensile strength after 5 complete cycles of printing, shredding, and re-extruding. We're only adding 1/2 of 1 cycle, so I think we'll be just fine. And frankly, it will be well worth that sacrifice if it makes this filament actually usable and reliable enough for large 3D printed projects. There's just one issue. Doesn't it add more labor? Well, say hello to my little friend. This, boys and girls, is the ArtMay Pelletizer, a mostly 3D printed beast of a machine that can turn a kilo of filament into these perfectly sized pellets in a matter of minutes. Simply attach your drill, clamp the drill's trigger, and put on your favorite noise-canceling headphones. That part's important. Here's why. But the question is, will this filament now actually be consistent enough to print reliably? Or will all the corners that we're cutting, such as skipping the entire drying process altogether, come back to bite us? To test it out, I extended a spool to support 3 kilos, loaded up a ton of raw regrind, and lowered my expectations. But annoyingly, the filament that came out was good, like really good. We're talking 180 meters of darn near perfect filament before the extruder even clogged. I wish I could tell you why, when I want to print junk filament just for pelletizing, it turns out beautifully, but in the past, when I've tried to print the good stuff, it comes out bumpier than my cheeks during puberty. It's possible that the material on top of the pile was freshly shredded since I upgraded and rebuilt the shredder, leading to fewer impurities and less moisture. It's also possible that after 2 full years of optimizations and learnings, I've just improved my shredding, sifting, and extruding workflows. I really want to believe it's that. But honestly, I don't know. So I just kept extruding and extruding and extruding until I had plenty of filament to be pelletized. Then I loaded up the first spool and let her rip. But as I was pelletizing all of this freshly extruded filament, one thing was really bothering me, a thought that I just couldn't shake. As I watched the filament go into the pelletizer, it was clear to me that something like 99.8% of it was good enough to print. In other words, there was one little tiny 2mm bump every 10 meters or so, sometimes even less frequently. And so it really felt like a damn shame to commit the extra time, labor, and energy costs to re-extruding the entire spool when most of it was absolutely fine. Now that thought planted a seed in my mind that would bloom into a full-blown breakthrough later on. But first, it was time to try re-extruding these pellets to see if this workflow is perhaps the solution to all of our problems. Now, when I mentioned that I was going to experiment with this double extrusion process, David over at ArtMay actually did recommend that I should change to the low compression screw for pelletized filament. But honestly, that's a whole process that I'm just not realistically willing to do regularly as part of this workflow. So we're just gonna have to try and make this work with the high compression screw that I normally use. Now, it probably doesn't come as much of a surprise, but because of the different behavior and profile of the re-extruded plastic, it did take a good bit of fiddling to get a more acceptable diameter. Specifically, I did have to reduce the temperature quite a bit, down to 170 degrees Celsius, which I'm really hoping isn't a reflection of the polymers degrading. Ultimately, I did still end up with undersized filament that averaged around 1.65 millimeters, but I would much rather be undersized and increase the extrusion multiplier on the printer than oversized and jam the extruder. But still, the filament wasn't perfect. I mean, sure, we'd gone from one blob every 10 meters or so to every 50 meters or so, but all it takes is that one blob to ruin an entire print, which means that this filament is still not reliable enough for real-world use. Which brings me back to that seed of an idea that was planted earlier. The idea that what if instead of trying to fix the bumps, we just avoided the problem altogether? Now, I don't know about all of you, but I keep getting targeted by a ton of these YouTube shorts for this company Infinity Flow. So basically, they've created a product for print farms which detects when your filament runs out and then feeds another spool into the printer seamlessly. But unlike an AMS, the printer doesn't actually need to know what's happening or have a filament cutter or any of that for this to work. The Infinity Flow just feeds and the printer carries on, none the wiser. What's more, they've recently been showing off an inline filament cutter that uses simple physics to automatically cut the filament when a bend or a piece of tape jams it. Now, apparently this is based on a free and open source design by Hackman over on MakerWorld. So here's what I'm thinking. What if, instead of relying on unreliable jam detection on the 3D printer and then manually unloading and reloading the printer, we just set up a cutter to snip the bumpy section before it ever causes a jam? From there, and this is the important part, we could either use something like the Infinity Flow or just any AMS with endless spool functionality, or the upcoming Panda Bamboo feeder from BQ to just auto-load another spool of recycled filament without a hitch. Now, on the upside, this could theoretically work on any printer without needing to modify it, and it solves the reliability issue. On the downside, it can get a bit expensive, at least if we go the Infinity Flow route. But considering that millions of people, myself included, already have 3D printers with an AMS, it might just be the best way forward. So to test it out, I printed off one of these HAFC designs, spent a few minutes assembling it with maybe $6 worth of AliExpress parts that I already had around the studio, and tested it out. Okay, guys, I'm back. Look at this. I just built this thing. It's like a few bucks worth of parts, okay? It took me like 20 minutes to assemble. We've got some filament here, all right? Let's see if we can find a bump just to demonstrate. Now, in order to like actually really get it to work, I would have to machine this piece so that this becomes the stopper. So I need this hole to be exactly 1.75 or as much as the printer can take. Now, let's find a bump. Oh my God, I'm so excited about this. Hold on. You see what I mean? How this filament is 99.9% good? Like, you really have to go looking for a bump. All right, there's a big bump. So you feed this through, a bump comes, it cuts the filament perfectly, cleanly, with little force, lets it go. Now imagine you had a couple of these, okay? And then you just went back and forth and the printer kept going. Is that a bummer? Yeah. But imagine if we just had the infinity flow thing on there and it just went back and forth and back and forth, and maybe you could rig it up to beep, and then all I have to do is pull that out, cut this off, load it up, and then we can use this. You could use this filament now on any printer that has an AMS and just load it. But so freaking excited. Okay, let's go test it on a printer. Okay, so super promising first attempt. I did try this out on a Prusa Core 1 just because it was the only printer that happened to be running a 0.6mm nozzle, and this thing works flawlessly. Even though I haven't yet created a proper 1.75mm die, the internal geometry of the Bowden coupler thing already acts as a pretty good filter. It cuts the filament at the first sign of any bump, and the printer pauses when the filament runs out. Don't mind this print failure. The nozzle on the printer did still clog, but like I mentioned before, I actually really don't mind if we can only use my recycled filament on a 0.8mm nozzle, so no big deal. But what do you guys say we go ahead and print off some more of these things and test the setup on a printer with endless spool functionality? All right, I'm back. It's been a few days and I've been experimenting a lot. So first of all, the cutter idea is indeed very, very promising. I have been able to reliably print some very, very big stuff with recycled filament just by relying on filament runout detection and this thing. Now, sometimes it does give you false positives, so I am testing out some potential solutions. And I also spoke with Hackman 3D, and he is about to release a V2 of this that should be out by the time you guys see this video. Plus, he's also working on fixing and adding an adjustable cutting threshold in version 3, so that's really good. Now, the only problem is, as it stands right now, using this on an AMS is kind of a bust. For one, the angle creates friction, which makes the false positives even worse. For two, all my printers with AMSs are configured to try to unload the filament whenever there's a break, rather than printing all the way through it. So either I need to tweak the macros and behaviors on my Box Turtle Voron, or I just need to get my hands on that pretty expensive Infinity Flow or the upcoming bamboo feeder thingy from Big Tree Tech. I do think that either one of those will probably be able to solve my problem by just seamlessly feeding the filament. Still, maybe I'm high on copium here, but I am pretty optimistic that this could be a central part of the solution to my problem. So, after about a week of testing and tweaking, where do we stand? Well, I have been at this far too long and been burned far too many times to make some kind of sweeping declaration that I've figured it out and all the problems are solved. Ultimately, the final workflow is probably going to be some combination of these different optimizations and hacks. But I do still feel like we have learned a lot in this video, and we've implemented some serious time-saving workflow optimizations. Plus, we've established some very clear next steps for either myself or some of you in the community to proceed from here. And that's a pretty fantastic outcome for citizen science like this. Now, one potential avenue is to continue experimenting with the whole shaving rig die idea. David from ArtMay did share this picture from one of his customers who has added many, many more dies with a much more gradual reduction down to 1.75 millimeters. And I'm pretty sure that that's gonna work a whole lot better. But it might also be interesting to explore the idea of putting an old CNC spindle or something on there with a set of gears to increase the torque, reduce the speed, and eliminate the need for a human being to stand there and hold a drill. But honestly, more than that, I'm actually really excited about the second opportunity, which is the idea of using smart 3D printing tech to just prevent these types of jams rather than trying to cure them. As you can probably tell by now, myself and a lot of others who have these machines have already put in a lot of time into trying to fix these kinds of imperfect extrusions. And if we can just make them a non-issue for the 3D printers going forward, then that is going to be a whole lot more convenient than adding all kinds of additional steps to the recycling process. I don't want to overplay it, but this was a major breakthrough for me, and I just can't stop thinking about that aphorism. The problem isn't the problem, it's your approach to the problem. At this point, I've spent years of my life trying to create the perfect recycled filament. And ironically, the best solution might just be to avoid the problem altogether. Why can't that be the solution to all of my problems? Third, I do think that I am going to continue experimenting with this whole re-pelletizing workflow. I might feel differently if I were optimizing for filament strength or cost savings rather than reliability and minimizing my labor input. But for me, I think it's going to end up being worth it if it makes me rely less on the filament cutter solution and require fewer of my interventions when actually printing the filament. I mean, sure, the resulting filament still isn't perfect, and it is inefficient from an energy standpoint to do this. But 99% of the time that I'm in the studio, both the extruder and the pelletizer are just sitting here. And it requires almost no attention or energy from me to fire them up every morning when I come into the studio. By doing so, I can gradually turn my entire bin of regrind into beautiful, perfect, and uniform pellets. Pellets which I could use for all sorts of interesting projects in the future. Which leads me to the final category of continued exploration that I'm excited about for future videos. I'm currently in talks with Creality to test out their M1 and R1 recycling products, and I'm really curious to see if their solution offers a more or less consistent result than the ArtMay, both with regrind and with my pellets. Additionally, I'm also in discussion with the folks at Plasticpreneur who do have an exciting new product coming out that could be a way more efficient way for using up my regrind, including the many, many kilos of hopelessly contaminated stuff that will just never be returned to filament. I don't know if I can talk about that, but do make sure you're subscribed if that sounds interesting. And who knows, maybe we'll get the opportunity to play with some pellet extruders and pellet extruder 3D printers in the very near future. One way or another, we have more than enough work ahead of us for another couple videos in this series, and I just really enjoy doing this stuff. So if you're interested in this and you've enjoyed this video, do make sure to get subscribed. Also, if you've missed any of the 7 videos that I've already done documenting the journey up until this point and what I learned, I will go ahead and link to the playlist with all of those videos right here. It's been a pretty incredible and interesting journey. Anyways, that's all for this week, but I'll see all of you on the next layer.